As you worked through the first page of this handout, you used what's known as the trapezoid method to approximate the area under a curve using just a few points on that curve. And we also focused on the fact that if that curve is a derivative, the area under it gives the change in the value of the function of which it is a derivative. When you use the trapezoid method to approximate, you make the assumption that the function you're finding the area under has a constant rate of change between the two endpoints of each subinterval that make the trapezoids. And we also talked about how this is equivalent to assuming that the value of the function over the entire interval is equal to the average of the values of the function at the endpoints of the interval. There are three other common methods of approximating area under a function. They still use a sampling of values of the function that we want the area under, but these methods use rectangles rather than trapezoids. The rectangle approximation methods are also known as Riemann sums. When you hear Riemann sums, think adding up the areas of rectangles. So we'll look first at the right endpoint rectangle approximation method, or right Riemann sum. In this method, instead of assuming constant acceleration over the interval, we assume zero acceleration. That is, we assume constant velocity over the interval, and we assume that the velocity stays constant at whatever its value at the right endpoint of the interval is. So for instance, if we look at the time from 7 to 7:03 in the same data set we were using on the previous page, we're going to assume that over that entire interval, the car was traveling at the speed which it had at the endpoint, 47 miles per hour. That means we approximate the velocity function by a horizontal line. And that will make the approximation for the change in position on this interval equal to the area of this rectangle. So we need to multiply the height of this rectangle, which is 47 miles per hour, by its width, which is 3/60ths of an hour. So delta position in that first interval, let's call it delta position A, is 2.35 miles. So this answer didn't happen to require any rounding, but let's just store it into alpha A, and then we'll have it there once we've calculated the changes in position on all of the other intervals. So pause the video now, do the change in position calculations for each of the 6 subintervals, and add all those up to see what approximation to the change in position you get using a right Riemann sum. The left endpoint rectangle approximation method is the same, except that we assume the constant value of the function is its value at the left endpoint of the subinterval rather than at the right endpoint. In this particular case, the function's value at the left endpoint of the first interval is 0. So assuming that value across the first 3 minutes gives a rectangle whose height is 0. So our delta position A in this case is 0. Looking at subinterval B, we're going to assume a constant velocity of 47 miles per hour from t equals 3/60ths to t equals 5/60ths. So that is that. And rectangle B will have a height of 47 miles per hour and a width of 2/60ths of an hour. So delta position B is 47 times 2/60ths. And we'll store that in alpha B. Go ahead and repeat for C, D, E, and F, and see what you get for the left Riemann sum approximation to the area under the velocity curve. The third common method is the midpoint rectangle approximation method, or midpoint Riemann sum. As the name implies, in this case, the constant velocity we assume is the velocity at the time that is at the midpoint of the interval. So note that with this data set, we are not going to be able to do 7 separate intervals because we don't know the time, say, at the midpoint between 7 o'clock and 7:03. There we would need 7:01 and 30 seconds. We don't have that time, so we can't do a midpoint approximation on that interval. If instead we look at this time interval from 7 o'clock to 7:10, this span on the graph, we can do a midpoint approximation because the midpoint in terms of time of that interval is 5/60ths, and we do have an approximation for the speed at 7:05. Similarly, if we look at the time interval from 7:10 to 7:20, the midpoint of that is 15/60ths, and we have a value for the velocity at 7:15. So when doing a midpoint Riemann sum with this data set, rather than having change in position on intervals A through F, we're just going to have estimates for change in position A and B, just 2 rectangles worth. The height of our first rectangle will be 67 miles per hour, and its width is 10/60ths of an hour. So delta position A is 67 times 10/60ths, or 67 divided by 6. Units there are miles. So now you should be able to find the change in position using rectangle B, add up the 2 results, and you will have the midpoint Riemann sum for this data set using 2 rectangles and subintervals of width 10/60ths.